XHHW cable is often a cost-effective option for underground electrical service installations due to its inherent durability and excellent resistance to moisture. When weighed against other types of underground rated cables, XHHW typically presents a lower initial investment, making it an attractive choice from a budgetary standpoint. Utilizing 4-inch PVC conduit is generally sufficient for housing a 250 mcm XHHW cable. The National Electrical Code (NEC) mandates that handholes must have a bottom to prevent the accumulation of water. However, there are specific exceptions where handholes without a bottom may be permitted. These exceptions are granted under specific circumstances. Firstly, the cable is enclosed in a separate jacket or conduit within the handhole itself. Secondly, the handhole provides adequate drainage to effectively prevent any pooling of water inside the enclosure. XHHW cable is an insulated cable and is generally suitable for installation within handholes. To ensure compliance with the NEC exceptions and to maintain a safe and code-compliant installation, certain requirements must be meticulously followed. Firstly, the cable must be enclosed within a separate protective jacket or conduit specifically within the handhole. Secondly, the handhole must have adequate drainage provisions to prevent water accumulation. There are also additional factors to consider during the installation process. Firstly, it is essential to ensure that all conduits are properly sealed at the handhole entrances to prevent water from entering the system. Secondly, install a ground rod in close proximity to the handhole to provide proper grounding for the electrical system. Thirdly, and most importantly, adhere to all applicable codes and regulations, including any specific local requirements in addition to the NEC guidelines. In conclusion, using XHHW cable within a 4-inch PVC conduit system is both an economical and approved solution for underground electrical service, especially when handholes are located at both ends of the run. This is conditional, provided that the previously mentioned requirements regarding the handhole bottom and cable protection are strictly adhered to. Remember to check with your local jurisdiction as interpretations of the NEC may vary. For the handhole requirements, the National Electrical Code Article 314.30 C covers the requirements for handholes and manholes. It states that handholes and manholes shall be designed and installed to avoid the entrance of water or the accumulation of moisture. Access should be provided to all equipment. Metal covers and other exposed conductive surfaces shall be bonded or grounded. Article 314.30 C1 discusses the covers. Covers of handholes or manholes shall have sufficient strength to sustain the loads likely to be imposed on them. Article 314.30 C2 covers the pull iron or hardware. Pulling irons or other hardware shall be installed and arranged to avoid damage to the cable. Article 314.30 C3 covers the cable supports. Cable support shall be installed where cables are arranged in multiple tiers. The NEC does not specifically prohibit handholes without bottoms, but it emphasizes preventing water accumulation. If the handhole lacks a bottom, proper drainage is crucial to comply with 314.30 C. Ensuring adequate drainage prevents moisture buildup, which can damage cables and create safety hazards. Local amendments to the NEC can further regulate handhole construction, so checking local codes is essential. XHHW cable is suitable for wet locations, as indicated by its designation, which stands for cross-linked polyethylene high heat resistant and water resistant. The cross-linked polyethylene insulation provides excellent moisture resistance, making it appropriate for direct burial and underground applications. However, even with XHHW's moisture resistance, additional protection inside the handhole is advisable to ensure longevity and reliability. Using a separate jacket or conduit within the handhole provides an extra layer of protection against physical damage and moisture exposure. This added protection is particularly important in handholes without bottoms, where the risk of water and debris ingress is higher. The size of the PVC conduit, 4 inches, is generally adequate for a 250 mcm XHHW cable, but it is important to verify the conduit fill requirements based on the NEC. The NEC specifies the maximum allowable fill for conduits to prevent overheating and to facilitate easy cable pulling. Chapter 9, Table 1 provides the percentage of cross-section of conduit and tubing for conductors. Chapter 9, Table 4 details dimensions and percent area of conduit and tubing. Chapter 9, Table 5 covers the dimensions of insulated conductors and fixture wires. NEC Chapter 9, Note 9 to Table 1 notes that for conductors not included in Chapter 9 such as compact or high-temperature conductors, the actual dimensions used shall be permitted. The conduit fill is calculated based on the cross-sectional area of the conductors and the inner diameter of the conduit. For a single conductor in a conduit, the allowable fill is 53% per NEC Table 1. When multiple cables are installed, the fill percentage decreases. To calculate conduit fill, determine the total cross-sectional area of the conductors and divide it by the internal area of the conduit. The resulting percentage must be below the maximum allowable fill percentage specified in the NEC. For a 4-inch PVC conduit, the internal area can be found in NEC Chapter 9, Table 4. Ensure that the calculated fill percentage does not exceed the NEC limits. If the conduit fill is too high, consider using a larger conduit size or reducing the number of conductors in the conduit. The installation of a ground rod near the handhole is essential for proper grounding of the electrical system. Grounding helps to protect against electrical shock and to provide a path for fault current to flow back to the source, tripping the circuit breaker or fuse. According to NEC Article 250, grounding electrodes must be installed and connected to the grounding electrode system. A ground rod, typically made of copper or copper-clad steel, is driven into the earth to provide a low-impedance path to ground. The ground rod should be installed as close as practical to the handhole to minimize the length of the grounding conductor. The grounding conductor, which connects the ground rod to the electrical system, must be sized appropriately based on the size of the service entrance conductors. NEC Table 250.66 provides guidance on the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding conductor should be securely connected to the ground rod using a listed connector. The connection must be protected from corrosion and physical damage. In addition to the ground rod, other grounding electrodes may be required, such as a metal water pipe or a building steel. The grounding electrode system should be interconnected to form a comprehensive grounding network. Proper grounding is critical for the safety and reliability of the electrical system. The NEC provides detailed requirements for grounding to ensure that electrical systems are properly grounded and protected against faults. Sealing the conduit entrances at the handhole is important to prevent water from entering the conduit system. Water ingress can damage the cables, reduce their lifespan, and create electrical hazards. To seal the conduit entrances, use a suitable sealant that is compatible with conduit and cable materials. Duct seal is a commonly used sealant for this purpose. It is a non-hardening, pliable compound that provides a watertight seal. Apply the sealant liberally around the conduit entrance to ensure a complete seal. Push the sealant into any gaps or voids to prevent water from seeping in. In addition to sealant, conduit hubs or fittings with watertight seals can be used to provide a more robust seal. These fittings are designed to prevent water from entering the conduit system. Ensure that the fittings are properly installed and tightened to provide a watertight seal. Regular inspections of the conduit seals should be conducted to ensure that they remain intact and effective. If any damage or deterioration is observed, the seal should be repaired or replaced promptly. Proper sealing of the conduit entrances is an essential step in protecting the electrical system from water damage. When installing cables in underground conduits, it is important to use proper pulling techniques to avoid damaging the cables. Cables can be damaged by excessive tension, abrasion, or bending. To minimize the risk of damage, use cable pulling lubricant to reduce friction between the cable and the conduit. The lubricant should be compatible with the cable and conduit materials. Feed the cable into the conduit slowly and steadily, avoiding any sudden jerks or pulls. Use pulling equipment, such as a cable puller or winch, to apply a consistent and controlled pulling force. Monitor the pulling tension to ensure that it does not exceed the cable's maximum pulling tension rating. If the pulling tension is too high, stop pulling and investigate the cause. It may be necessary to use a larger conduit size or to reduce the number of bends in the conduit run. Avoid sharp bends in the conduit run, as these can increase the pulling tension and damage the cable. Use sweeps or long radius elbows to minimize the bending radius. If necessary, use intermediate pull boxes or handholes to break up long conduit runs and reduce the pulling distance. Follow the cable manufacturer's recommendations for pulling tension and bending radius. Proper cable pulling techniques are essential for ensuring the long-term reliability of the electrical system. Local codes and regulations may have additional requirements for underground electrical installations. It is important to consult with the local authorities to ensure that the installation complies with all applicable codes and regulations. Local codes may specify requirements for conduit depth, backfill materials, and grounding. They may also have restrictions on the type of cables that can be used in underground installations. Failure to comply with local codes can result in fines, delays, and rework. It is always best to check with the local authorities before starting any electrical work to ensure that the installation is code compliant. The NEC is a comprehensive set of standards for electrical installations, but it is not a substitute for local codes and regulations. Local codes may be more stringent than the NEC in certain areas. Therefore, it is important to comply with both the NEC and local codes. The NEC is updated every 3 years, so it is important to use the latest edition of the code. Local codes may also be updated periodically, so it is important to stay informed of any changes. Compliance with the NEC and local codes is essential for ensuring the safety and reliability of electrical installations. In summary, when installing XHHW cable in underground service with handholes, remember to address the following points. Firstly, ensure handholes have proper drainage or meet NEC exceptions for bottomless designs by providing a separate jacket or conduit for the cable within the handhole. Secondly, verify that the 4-inch PVC conduit is adequately sized for the 250 cm XHHW cable, considering conduit fill requirements. Thirdly, install a ground rod near the handhole and properly ground the electrical system in accordance with NEC Article 250. Fourthly, seal conduit entrances to prevent water ingress using appropriate sealants or watertight fittings. Fifthly, use proper cable pulling techniques to avoid damage to the cable during installation. Sixthly, comply with all applicable local codes and regulations in addition to the NEC requirements. Finally, conduct regular inspections to ensure the ongoing integrity of the installation, including conduit seals and grounding connections. By adhering to these guidelines, the underground service installation will be safe, reliable, and compliant with industry standards and regulations. Remember that electrical work can be dangerous, so it is always best to consult with a qualified electrician if you are not comfortable performing the work yourself. The NEC provides specific guidelines for working space around electrical equipment. These guidelines are designed to ensure that electricians have enough room to safely work on electrical equipment without being exposed to hazards. NEC Article 110.26 specifies the requirements for working space about electrical equipment. The working space must be clear and unobstructed. There must be enough space to open doors and access equipment. The depth of the working space depends on the voltage of the equipment and the presence of exposed live parts. The width of the working space must be at least 30 inches, or the width of the equipment, whichever is greater. The height of the working space must be at least 6 feet 6 inches, or the height of the equipment, whichever is greater. The working space must be adequately illuminated. The NEC also specifies requirements for access to working space. There must be at least one entrance to the working space. The entrance must be large enough to allow a person to enter and exit easily. The entrance must be kept clear and unobstructed. In addition to the NEC requirements, local codes may have additional requirements for working space. It is important to consult with the local authorities to ensure that the installation complies with all applicable codes and regulations. Proper working space is essential for the safety of electricians and for the proper maintenance and repair of electrical equipment. When working on electrical equipment, it is important to follow all safety precautions. Always to energize the equipment before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards of working with electricity. If you are not comfortable working on electrical equipment, consult with a qualified electrician. The ampacity of a conductor is the maximum current in amps that the conductor can carry continuously under specified conditions of use without exceeding its temperature rating. The ampacity of a conductor is determined by several factors, including the size of the conductor, the type of insulation, the ambient temperature, and the number of conductors in a raceway or cable. The NEC provides tables of ampacities for various types of conductors. NEC Table 310.16 lists the allowable ampacities of insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth, based on ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit. The ampacity of a 250 mcm XHHW conductor is 255 amps when the ambient temperature is 30 degrees Celsius, 86 degrees Fahrenheit, and there are not more than 3 conductors in a raceway or cable or earth. If the ambient temperature is higher than 30 degrees Celsius, 86 degrees Fahrenheit, the ampacity of the conductor must be derated. NEC Table 310.15 B2 provides adjustment factors for ambient temperature. If there are more than 3 conductors in a raceway or cable, the ampacity of the conductors must be derated. NEC Table 310.15 B3 provides adjustment factors for the number of conductors in a raceway or cable. The ampacity of a conductor is an important consideration when designing an electrical system. The conductors must be sized so that they can safely carry the expected load current without overheating. Overheating of conductors can damage the insulation and lead to electrical fires. It is always best to consult with a qualified electrician to ensure that the conductors are properly sized for the application. Voltage drop is the decrease in voltage that occurs along a conductor due to the impedance of the conductor. Voltage drop is an important consideration when designing an electrical system because excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop on feeder circuit should not exceed 3% and that the voltage drop on branch circuit should not exceed 5%. To calculate voltage drop, use the following formula: voltage drop equals current times resistance, where current is the current flowing through the conductor, and resistance is the resistance of the conductor. The resistance of a conductor depends on the length of the conductor, the cross-sectional area of the conductor, and the resistivity of the conductor material. The resistivity of copper is 1.724 times 10 to the negative 8th power ohms meters at 20 degrees Celsius. To reduce voltage drop, use larger conductors or shorten the length of the conductors. It is also important to ensure that the connections are tight and that the conductors are properly terminated. Excessive voltage drop can cause a variety of problems, including reduced lighting levels, reduced motor torque, and increased equipment heating. It is always best to consult with a qualified electrician to ensure that the voltage drop is within acceptable limits. The short circuit current rating (SCCR) of an electrical component is the maximum short circuit current that the component can withstand without being damaged. The SCCR is an important consideration when selecting electrical components because it helps to ensure that the components can safely withstand the high currents that can occur during a short circuit. The SCCR of an electrical component is typically marked on the component's nameplate. The SCCR is expressed in amps. The SCCR of an electrical component must be greater than or equal to the available short circuit current at the point where the component is installed. The available short circuit current is the maximum short circuit current that can flow at a given point in an electrical system. The available short circuit current can be calculated using various methods, such as the point-to-point method or the infinite bus method. If the SCCR of an electrical component is less than the available short circuit current, the component may be damaged during a short circuit. This can lead to equipment failure, fire, and electrical shock. It is always best to consult with a qualified electrician to ensure that the electrical components are properly selected and that the SECR of the components is greater than or equal to the available short circuit current. Proper overcurrent protection is essential for protecting electrical systems from damage due to overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. The NEC provides detailed requirements for overcurrent protection. NEC Article 240 covers overcurrent protection. The overcurrent protection device must be sized to protect the conductors that it is protecting. The overcurrent protection device must have an interrupting rating that is greater than or equal to the available short circuit current at the point where it is installed. The overcurrent protection device must be readily accessible. The overcurrent protection device must be properly labeled. Circuit breakers are automatic overcurrent protection devices that can be reset after they have tripped. Fuses are non-automatic overcurrent protection devices that must be replaced after they have blown. The choice between circuit breakers and fuses depends on the application and the specific requirements of the electrical system. Proper overcurrent protection is essential for the safety and reliability of electrical systems. Ground fault protection is designed to protect people from electrical shock hazards caused by ground faults. A ground fault occurs when current flows from a live conductor to ground. Ground fault protection devices, such as ground fault circuit interrupters, GFCIs, and ground fault equipment protection, GFEP, are designed to detect ground faults and to interrupt the flow of current before a person can be injured. GFCIs are typically used in residential and commercial applications to protect people from electrical shock hazards in wet locations, such as bathrooms, kitchens, and outdoor areas. GFEP is typically used in industrial applications to protect equipment from damage caused by ground faults. The NEC requires ground fault protection in certain applications. NEC Article 210.8 covers ground fault circuit interrupter protection for personnel. NEC Article 230.95 covers ground fault protection of equipment. Ground fault protection is an important safety feature that can help to prevent electrical shocks and injuries. Electrical enclosures are designed to protect electrical equipment from the environment and to protect people from electrical shock hazards. Electrical enclosures are available in a variety of sizes and shapes to accommodate different types of electrical equipment. Electrical enclosures are typically made of metal or plastic. Metal enclosures provide better protection from physical damage and electrical shock hazards. Plastic enclosures are lighter and more resistant to corrosion. The NEC specifies requirements for electrical enclosures. NEC Article 314 covers outlet boxes, conduit bodies, and handhole enclosures. Electrical enclosures must be properly grounded. Electrical enclosures must be sized appropriately for the equipment that they contain. The electrical enclosures must be suitable for the environment in which they are installed. Electrical enclosures are an important safety feature that can help to protect people and equipment from electrical hazards. Cable trays are used to support and route electrical cables in industrial and commercial applications. Cable trays are available in a variety of sizes and materials. Cable trays can be made of steel, aluminum, or fiberglass. Cable trays can be ladder type, ventilated trough type, or solid bottom type. The NEC specifies requirements for cable trays. NEC Article 392 covers cable trays. Cable trays must be properly supported. Cable trays must be grounded. Cables installed in cable trays must be properly secured. Cable trays must be suitable for the environment in which they are installed. Cable trays are a cost-effective and efficient way to support and route electrical cables in many applications. Flexible metal conduit FMC is a type of conduit that is used to protect electrical conductors. FMC is flexible, which makes it easy to install in tight spaces and around bends. FMC is typically made of steel or aluminum. FMC is available in a variety of sizes. The NEC specifies requirements for FMC. NEC Article 348 covers flexible metal conduit. FMC must be properly supported. FMC must be grounded. Conductors installed in FMC must be properly secured. FMC must be suitable for the environment in which it is installed. FMC is a versatile type of conduit that can be used in a variety of applications. Liquid-tight flexible metal conduit, LFMC, is a type of conduit that is similar to FMC, but it has a liquid-tight jacket. The liquid-tight jacket protects the conductors from moisture and other contaminants. LFMC is typically made of steel or aluminum. LFMC is available in a variety of sizes. The NEC specifies requirements for LFMC. NEC Article 350 covers liquid-tight flexible metal conduit. The LFMC must be properly supported. LFMC must be grounded. Conductors installed in LFMC must be properly secured. LFMC must be suitable for the environment in which it is installed. LFMC is a good choice for applications where the conductors need to be protected from moisture or other contaminant. Electrical drawings are used to communicate the design of an electrical system. Electrical drawings typically include a site plan, a floor plan, a one-line diagram, a panel schedule, and a bill of materials. The site plan shows the location of the electrical equipment and the property. The floor plan shows the location of the electrical outlets, lights, and other electrical devices in the building. The one-line diagram shows the electrical connections between the different components of the electrical system. The panel schedule shows the circuit breakers in each electrical panel. The bill of materials lists all of the materials that are needed to install the electrical system. Electrical drawings are an important tool for electricians and other electrical professionals. They help to ensure that the electrical system is installed correctly and safely. Electrical testing is used to verify that an electrical system is installed correctly and that it is operating safely. Electrical testing typically includes continuity testing, insulation resistance testing, ground resistance testing, and voltage testing. Continuity testing is used to verify that the electrical connections are continuous and that there are no open circuits. Insulation resistance testing is used to verify that the insulation on the conductors is in good condition and that there are no ground faults. Ground resistance testing is used to verify that the grounding system is properly installed and that the resistance to ground is low. Voltage testing is used to verify that the voltage levels are correct and that there are no voltage drops. Electrical testing is an important part of any electrical installation. It helps to ensure that the electrical system is safe and reliable.